Alright guys, welcome back, and today we're going to be going over 5.6, which is the law of sines. And for our think/warm-up here, I have, can we use SOHCAHTOA on non-right triangles? And the answer is simply no, right? The ratios are only, the trigger ratios that we have with SOHCAHTOA, opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent, they only work if we have right triangles. But the important distinction here is just because SOHCAHTOA can't work on non-right triangles doesn't mean that like the sine, cosine, and tangent can't be used if we don't have a right triangle. It's just if we have a right triangle, then we have ratios that are the same every single time. But the sine of 33 degrees, let's say, is the sine of 33 degrees no matter where it's at. Right? So we can still use trig, and a good example here is the law of sines, and this is something that you absolutely want to write down. So let triangle ABC be any triangle, and that's really important. Any triangle doesn't need to be a right triangle. Any triangle with A, B, and C representing the measures of the sides of the opposite angles with the measures A, B, and C respectively, then the following is true. And so we have A, which is these are all sides of a triangle, and then each one of these are the opposite angles. Of those sides, right? And the sine of them. That's why it's called the law of sines. And we'll get into exactly why that is right now. So, and it goes over it in your book, and I'm going to just make sure I have the same layout as your book. Your book calls this A, this one B, and this one C, and we just say we have center O. And then what your book does is we can draw a diameter through the center from B, and let's just call this point D, right? And we have our center O here still. And let's call this whole distance here 2R, right? The diameter, or 2 times the radius. But since I'm already using D here, I'm going to call it 2R instead. And now notice if we connect, I'll get another line. If we connect D and A there, then right here, I'll do it in red instead, right here, we have a right angle. And that's something that you might remember from geometry, right? If you have a triangle inscribed in a circle, with its hypotenuse being the diameter, then you get a right triangle. And so the right triangle is something that we can absolutely use sine, cosine, and tangent on, right? So, and notice these two angles, I'll mark this one in blue, these two angles are the same, D and C. And why are they the same? And that's because they both intercept this same arc. Can't see what I'm drawing. This same arc. Since they both intercept that arc, those angles are the same. And so what does that tell us? That tells us that since they're the same angle, that sine of D equals the sine of C, right? Well, now let's look at what the sine of D is. This would be across from C, we have little c. Across from B, we're going to have little b, and across from A, we're going to have little a. This should actually be B, this longer side. And now we have sine of D is opposite over the hypotenuse, which in this case is going to be, the opposite is C, and the hypotenuse is 2R. Well, we just said that the sine of D is the same thing as the sine of C, so let me replace it. So the sine of C equals C over 2R. And then we're just going to do a little algebraic switch here. And if we multiply this 2r over and then divide the sine of c over, then we're going to get 2r equals c over sine of c. And you might be thinking, well, what's the point of that? And so if we were to do the same thing, if we were to go from point A and we drew a diameter through and then labeled a point, and then we did the same thing with C here, and we went through, I'm a little off, we went through the center and the diameter and made another point there, what we would end up getting, I'm not going to do it 3 different times because it's all the same concept. What we would end up getting is we would end up getting 2r equals a over sine of a, and we would get 2r equals b over sine of b. And what does that tell us? Well, since they're all 2r, they're all also equal to each other, which brings us back to our formula here. So that's how we get it. And now, this one I don't think is too bad to memorize, although you definitely want to write it down. But it's definitely intuitive. We have a over the sine of a, b over the sine of b, and c over the sine of c, all equal to each other. And if you wanted to, you could flip them the other way around, right? You could have sine of a on top. You could have the angles on top and the sides on bottom if you want. Well, let's go through an example. So example 1, solve triangle ABC if A equals 33 degrees, B equals 105 degrees, and B equals 37.9. So your book, in the problems it gives you, does not draw the triangles for you. So I'm just going to do a rough sketch. I know A is 33 degrees. That's pretty tight. And then maybe B is over here. So that's angle A. B is 105, which is greater than 90. Let's just go out that way. And maybe that's the triangle. Who knows, right? I'm just making a rough guesstimate. So that's going to be B. We know this is 33 degrees. We know this is 105 degrees. And then if that's AB, that has to be C. And we know that B is across, that will be 37.9. And then we can call this CA. And so when it says solve the right triangle, we have to find any missing components. So the one that I think is the easiest here is to find this angle C. Angle C is simply going to be 180 degrees minus the other two. So minus 33 minus 105. And that's 75 once you take away 105, and then 75 minus 30 is 42 degrees. So we have angle C is 42 degrees, and we can stick that right there, 42 degrees. And so that's part of our solving. And now we just need the other two sides. And let's just use the law of sines that we have. And the first one that comes to mind is I have what angle B is and the side B. So I'm going to write that one first. And so that'll be 37.9 all over the sine of B. And then we know, that the sine of B, we know angle B is 105 degrees given to us. And then we know that C over the sine of 42 degrees is 1. And so we could just multiply that sine of 42 degrees over. We get C equals 37.9 times sine of 42 degrees all over sine of 105 degrees. And that's just something you stick in your calculator. And once you stick that in your calculator, you should get that C is about 26.25. And now we just have to do the same thing for A. And again, we know that 37.9 all over the sine of 105 degrees is equal to, well, now we follow the law of sines for the other one. And we're looking for A, and that'll all be over the sine of A, but we know angle A is 33 degrees, so that'll be sine 33 degrees. And again, from here we just solve, multiply the sine of 33 degrees over, and we'll get A equals 37.9 times the sine of 33 degrees all over the sine of 105 degrees. And that is, again, something you just punch into your calculator. And once you do that, you will get that A is about 21.37. And I recommend punching these out of your calculator to make sure that you can actually get these correct answers, so that, come a quiz or any other homework, when you have to do it on your own, you are sure that you know how to use your calculator correctly. And if you don't, you could always ask me. So that's going to wrap up our first section of the law of sines. Again, it's really just following this formula and plugging stuff in. So, and a good thing to remember also is that what we call our angles are usually the capital letters. So we have capital A, B, and C, and then usually the sides, we do lowercase and we do the opposite side. So notice we have big angle C in the top right, and then across from it is our side length little c. But that is going to do it for the first part of 5.6.